This is the third week, okay? In the third week, we will still discuss about first order system, and I would like to review on the disturbance case, yeah? So we assume the disturbance is coming from the wind, and then the wind comes here as the force, but the force is unknown. And the first thing we do is to convert the differential equation into Laplace transform. So you see the Laplace transform on the right side. The first line showing the direct transformation, yeah, from the time domain to the Laplace domain. The first line on the right. The second line is the position. Okay, ZS. That's the position. The third line in here is the velocity. Notice here we have two inputs, yeah, one coming from the traction and one coming from the disturbance. Okay, and the block diagram showing the relationship of this one is given here. Okay, so ZVS is equal to TS minus FW of S multiplied by the transfer function. Yeah, and so this one is taken from MATLAB Simulink. So you can create blocks of vehicle controller and also the input disturbance, yeah, and then the junction here. All are available in the Simulink, which we can show later. Okay. Now, if you want to find out the transfer function from ZV over ZV star, assuming proportional controller and then disturbance is constant, we want to know whether this kind of controller is able to eliminate the effect of disturbance or not. Okay. So what we need to do is to express the transfer function, yeah, in terms of two inputs. The first input coming from the desired velocity ZV star. The second input is coming from the FW, this one, okay? Now, after your system is being closed loop, the closed loop already, yeah, the input coming to the system is the desired velocity, yeah. This is the whole system. However, when you are considering only the open loop system, where the plant and the traction is there, then your input is just traction and then the disturbance, yeah. But after you do the closed loop, this one closed loop, okay, closed loop, then your input is coming from the left here, yeah. And then the TS over here, the traction, is computed by the controller, yeah. Controller will compute the traction, which is why we will define a set of algorithm instruction to the controller, how the controller is going to process the error. Okay? Error is processed so that you can obtain the control signal, yeah. And then if we let the ks be constant, ZV star to be step function, in here disturbance is also considered as a step function, then we will use the final value theorem. Use final value theorem from here, yeah. Then we can obtain the asymptotic value of the ZV. Yeah, Nathan?
The ZV on the left, the superposition method.
Correct, superposition method. Yeah. This one is coming from the superposition method. Yeah. So you will obtain this term by assuming FW to be 0. Yeah, and then you obtain the below term here, assuming ZV star to be 0. That one also coming in your homework. Yeah, in your homework. Okay, next. Having seen the last line in here, we can see that the effect of FW or the disturbance is over here, yeah, the second term. And the second term will be small if we set the Kp to be high. But there is a limit of Kp that we can put to the system because Kp related directly to the traction. There is a limit of how big an engine we can put into the car, right? That's the limit. And then also there is a limit of how much traction you can put into the road from the tire. Now, what I want to discuss next is about simulation using MATLAB and Simulink. Yeah, this is what we want to discuss before we go to the second order system. We first discuss about TF, yeah, a function TF in the MATLAB. So TF is used to build a transfer function model, yeah. And what do you need here? You see in the syntax. So I copy this from the MATLAB Central. You can read it again from the MATLAB Central. If you search TF, this is what you will get. Okay, and you follow the syntax here. The sys equal to TF in the bracket numerator comma denominator. So what is that? So let's say our transfer function GS is expressed as numerator divided by denominator. It is always like that, right? So we have a fraction. Yeah, transfer function is always a fraction. So in the MATLAB, we express num and den as polynomials. You also know that it is polynomials, right? We have 3s squared plus 5s plus some constant. So that is actually polynomial in S. Okay. So how do we express polynomial in the MATLAB? Anyone know? No. Yeah, we just type in a polynomial format, which it's actually this one. You write polynomial like this, like it's like a vector, yeah, a vector. So let's say you have a numerator of 2s plus 5. Yeah, the power of 1 is you put here, multiply by a constant 2. The power 0 you multiply by 5. Okay. And then what about the denominator? 3s squared, yeah. So the power 2 multiply by 3. Do we have power 1? No, so we put it 0. Okay. And then the power 0 is 10, so you put 10 on the third term over there. Okay. And so you just write sys tf num comma den. Yeah, by the way, the sys over there, sys, it could be any letter. Yeah. It doesn't have to be sys. Yeah, it's a variable that you define. But you define it so that you know that it is my system. So up to you on how you recognize it. Okay. After we get our transfer function in the MATLAB, we want to simulate it. Yeah, we will not just leave it there and then going home. No, no. We create the transfer function model in MATLAB so that we can do simulation, right? So how do we simulate it? The easiest way is using LSIM. LSIM stands for linear simulator. L coming from the linear, because the transfer function that we have is a linear system. Yeah. So this is the syntax. Very easy. You put your sys first and then your control input and then the time array that you want to simulate. The time array is free. You define it up to you. Okay. As an example, I give over here, I set first the time frame, yeah, from 0 to 10 but in increment of 0.01. That's the increment. And then this is the transfer function earlier, numerator and denominator. What I want to remind you here is that if we use transfer function and we use LSIM, yeah, we can only simulate the system without initial condition. Yeah, never tried it yet, I think. Yeah, so this is the first time you see it. So how do we specify input to the system? You just define any kind of input. Let it be sinusoid, step input, or is it indicator function? Indicator function like this one. Yeah, like this. You just have to specify it. In this case, let us define unit step function. Just to define unit step function, we just write ones of size t. Okay. The ones of size t will return what? What will method do if we write this? Huh? Not 1010. We say once at the size of t. That means if we write down, sorry, I press it. If we write down once and bracket 5, this will result in 1, 1, 5, 1, 2, 3, 4, 5. It's a vector. It's an array. Okay.
Also,
Yeah, because we want it once. That's so all of them will be 1. Okay, and this is the number of points. Okay, and if we specify in the bracket the size of t, then we will have an entry of 1 as much as the vector t here. So we do that because the LSIM wants you to specify u and t that has the same number of elements, same number of points. If the number of points are different, LSIM will not accept it. Yeah. Then you do this, x is equal to, you can replace it with y, z, anything. Yeah. This will give you the result, and then you can plot the result. Okay. So you can check this later in your computer. You do this. Why am I telling you to use MATLAB to check the simulation? It is so that you have your own laboratory in the MATLAB. Okay. Sometimes the control system theory is hard to understand because we don't have a system that we can play with. Okay. But with this, at least you can build a model in your computer and see what's going on if you change this and that. Okay. So what if I want to make a closed loop transfer function then? Can we simulate the closed loop transfer function using LSIM? Any idea? So what to do? Yeah, that means you just have to replace the numerator and denominator with the closed loop transfer function. Okay. So you write down what is the closed loop transfer function first. Yeah, let's say we know that the g is 2s squared plus 5, 3s squared, sorry, not 2s, yeah, plus 10. Okay. So you have to first create the closed loop transfer function, okay, which is g like this. Once you obtain this, you obtain the new numerator and denominator, right? Yeah, you replace this into the MATLAB, and then you obtain your closed loop transfer function. You simulate again, that's your closed loop system response. Okay, so if we use the so-called M file, this is M file, yeah, M file editor, you have to write down the closed loop transfer function on your own. You write down the result. Yeah. But there is another way that we can do using Simulink. Yeah. So I have created in here two separated systems. The top one is using proportional controller only. The bottom one is using proportional and integral control. Okay. But then the vehicle model are the same, disturbance are the same, desired velocity are all the same. Then we want to compare them. The good thing using Simulink is that you don't have to compute the closed loop transfer function every time you change anything. Okay, you just have to double click this, change the value, and then run the simulation. Okay. And then when you run the simulation, there are many ways to see the result. You can using scope here, or you can output your simulation result to the workspace. By the way, do you know what is the workspace? Where do you find the workspace in the MATLAB? On the right side. usually in the command window, yeah. The command window, you get the workspace over there. So you can export it into the workspace and work on the MATLAB editor also, yeah. However, if you only want to use Simulink, you can use the scope to see the plot, okay. Do you want to know how do we compare this? Yeah, let's see the result lah. And before we see the result, there is one thing I want to tell you. You see that in the vehicle model, we specify M, C, right? And then KP, KI. There is no number on it yet. Okay. We can specify those in the callbacks. In the Simulink, there is a menu called callbacks, where you can specify the initialization function. So the model is initialized by all of these data. The M, C, KI, KP, you set all of this. So when you set all of the M in here, all variable M in your Simulink change directly. You don't have to click all of the blocks, okay? And then you can also do another function after the simulation stop. Let's say when the simulation stop, you want to get the simulation data from the workspace, so this is what you do. Okay. This is not taken from example, I made it on my own. Okay. So if you want to ask me, you can ask me. I know how to do it. Okay. But you can also ask the MATLAB Central, all information are there. Yeah. So let's see the simulation result. This one, the result. Yeah. What we notice here, the proportional controller has a steady state error. Okay, although very small, we cannot see there is a steady state error coming from the proportional controller. The PI controller has zero steady state error. However, there is a overshoot. There is an overshoot over there. And this overshoot is very difficult to be eliminated. Yeah, that's one of the drawbacks. Well, what if we use PID then? We can also use PID where you use PID blocks available in the Simulink. Yeah, you see, I created the PI by just summing up KP and then KI over S, sum them up. However, you can also take out the PID block from the library, this one over here on the bottom. So in this case, I compared three systems, yeah, proportional on the top, proportional integral in the middle, and then PID on the bottom. Let us see how they perform. Of course, there is a, you know, there is a automatic tuning available in here. If you don't know how to tune it, you can press tune, and then MATLAB will compute the correct uh, P, I, and the D constant for you. Okay, and this is the result. For the PID controller, we can slightly reduce the overshoot, and then the steady state error is still zero. Okay. Any questions so far, Nathan? You mean this one? Yeah. PI and PID are they are the same.
So before you said that the P has an error, right?
Yeah.
What did you know that PI and PID is the true value?
They are the true value. No, because I know from the beginning when I see I compute the final value theorem from the closed loop transfer function, I know that the error is eliminated. Yeah. And then before I show you this graph, I compare the input and output together. Yeah, they are the same. So I know also. I check that.
So is it always the case that PI and PID is always good?
When you have step input, that's true. Yeah. But when you have a ramp desired input, that's not true anymore. Okay. So it really depends on what kind of signal that you want to follow. Yeah. Let's say, for example, Sobri and Ansel, you are running together. Yeah, running together. Ansel on the front, Sobri behind. And then Ansel is running with a constant speed, running constant speed. Sobri, can you follow constant speed? Can, right? What if Ansel is changing his velocity as he wish? Can Sobri follow asymptotically? No, I mean asymptotically, it's difficult, right? And that's the same with the controller. If you ask the controller to follow an arbitrary function, controller will not able to do it. Okay. All right. Now time for practice. This is warming up before the quiz. You derive the transfer function of the system. The input is the displacement you put here. The output is the displacement of this point. Come on. Wow. Derive the transfer function of the system where the input is the displacement of the point here, xi. The output is the displacement of this point. Yeah? Yeah. It's a spring. This is a spring. This is damper. Believe me, it is available in the module. If you read the module, you know where is it. Any course module have this. Yeah. UA's module from Anyco, it has the example. We don't have mass in here. Yeah? There is no mass. So if there is no mass, can we apply sigma force equal to m times A? No, we cannot do that. We can only apply force, balance force. Yeah, sigma force equal to 0. The force will be balanced. That's what we can write. There is no mass. So the force is balanced. When you pull it to the right, there is always a force that will cancel it out to the left. The force is trying to cancel out. You pull this right to the right, and then there will be a force because of the damper movement, and then because of the change in the spring length. Yeah. So we will analyze the force in here. Yeah, you analyze the force in here. Yeah, let us see. Let us see. Yeah, let us see. So we analyze the point in here. It's over there. Yeah. Okay. So there will be a force coming to the left from the damper. Okay. You see, this point is going to move to the right, right? And this point is going to pull the damper to the left. And because of that, the damper is going to resist. And the resistance from the damper is C times X dot. Okay. And then what about the force coming from the spring? It is the difference. Okay. It's how much the spring is being extended or being compressed. If the spring is extended, then the force will be coming in. If the spring is compressed, the force will be coming out from the spring. So that's the result. The force is assumed going to be to the right. Yeah, if we assume that xi is greater than x0. Okay, when the force is being when the spring is extended, yeah, then this point is going to moving to the right. Okay, the force is pulling it to the right. if the spring is being extended. Extended means the input displacement is greater than the output displacement. Yeah, this point will be pulled to the right. Say that again, xi minus x0. The velocity of this point. X0 dot is the velocity of this point. Yeah, what we can see from this diagram is that so the situation is like this. Yeah, this point is moving to the right with displacement xi. Yeah, and because of that, we assume that the output of this point is a displacement coming to the right. Okay, and you know this point is stationary. Yeah, so we want to know what is the force created from the damper when when the velocity of this is x dot. We know already that the force coming from the damper is just c times the x dot. Okay, yeah,
If I answer, do we get extra point?
is that a question?
Is this practice, or are you asking us to do it on the whiteboard and we can get extra point?
No, not on the whiteboard, but on the paper. If I see that you are correct, I will give you extra point. Do you have? Do you get it? Now you see it. You see it from the lecture notes. Is it?
Because so we do it.
Okay. So what's the answer?
C over K, sir.
C over k. What's the c over k?
Tau.
Uh, I'm not asking about the tau, but the transfer function of the system. But you answer on the tau.
Yeah, I thought you were.
No. I am asking you to derive the transfer function of the system.
Basically under K over.
Yeah, the transfer function of the system is what? Which one?
Over CS.
Yes, this one. Yeah, up to this point. Okay. Yeah. Any question? But you read from, yeah. Okay.
I just thought to do it.
Okay. Yes. Okay. After the quiz, let us discuss this. Yeah.
It's not like block diagram.
Not block diagram. No. We only need we only do uh you know force balance equation, like a free body diagram. Yeah. So we draw the free body diagram of this point. C is damper, spring constant.
But then it's a spring.
Yes, it is a const. It is a spring. Which one S?
CSXO.
This one. We take Laplace transform from here. Yeah.
Yeah. So the condition is the squeeze.
In this case, it's being extended. The spring is extended.
How do you know?
No, we assume it is extended. Yeah, we assume it is extended. So the force acting in this point is going to the right side. Okay. If it is being compressed, then the force will be going to the left.
Why the GXO go to the left?
It is always going to the left because of this condition. Yeah. Yeah. You are pulling this point to the right. The damper will surely resist it because this endpoint is fixed. Okay, it is fixed. So it's like let's say you 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 pull that. What do you feel? No, you hold it tightly. You pull it to the right, and then I pull it here. What do you feel? Yeah, that's my hand is the damper. You is that point. Okay, you try to move it to the right, and then I pull it to the left. So that's the force coming from my hand is coming from the damper.
Like the reaction force.
It's how the damper react to the situation. You hold it, no pulling yet, yeah. Do you feel anything? Now you pull it. That's how damper works.
Oh.
Okay. When you try to pull it, the damper is going to resist. Okay.
But if we push the damper,
will also push to the other direction. So you push it towards me. You push it towards me. That's how the damper works. Okay. Yeah. Okay. Let's move. Let's move again to the next topic. What about this one? The transfer function is from what? What do you think? Yeah, QI is input, and then Q0 is the output. Okay, the input here, the output is here. So how does the transfer function look like? You can also check it on the module. Yeah. So finally, we arrive also at first order system. Okay.
by exam we need to model, we need to do working from physical model.
Normally, no.
So you provide us with the GS.
Yeah, I normally provide it with the GS.
So no modeling.
Involved? No, no, no. Yeah. Normally, yeah. Under normal situation, no. But when your level is going up, I can give you the modeling problem. So if I don't give you the modeling problem, it means you are still beginner. Yeah, the first concept that we have here is that the Q0, the output, is determined by the height of the water. Okay, and then there is a resistance coming from the load valve, and then the A times H dot. What is this?
The velocity, the rate of water change of water.
The change of what?
The rate of the increase in water height.
Increase or decrease rate of changes. Okay, not just increase but rate of changes. Yeah, correct. So it is determined by input minus output. Okay, if input is bigger than output, increasing, right? If it is smaller, decreasing. That's correct. So only from here we derive the transfer function. Yeah, you replace the Q0 by H for R0. Yeah, Q0 you replace it by this. And then from here, you take Laplace transform. Laplace transform and then reorganize the terms. Okay, and then you finally, for this last step, you move all of this term to the right side. So it is 1 over AS plus 1 over R0. This is the set point, means the desired height that you will set after you perform closed loop feedback control. Not part of the plant, not part of the plant transfer function, but it will be the part of the closed loop transfer function, which I will show you in the next slide. Okay? In the block diagram. In the block diagram. It is in the block diagram. Yeah, try to imagine it. Yes. No, the input, right? Input coming from here. Input to the system.
What we know, the transfer function is Q0 over Qi.
You can certainly you can replace it the H with the Q0 because the R0 is constant. Okay, but then along the way we want to know whether we can control the H. Yeah, so we can replace with H in this case. Yeah, although we can also use Q. We can, depends on what we want to control. In this case, we are controlling the height of the water. Other case, you can also control the water flow. That's because the R0 here is constant. So 0 and then H, they are interchangeable. Let's say you find out the H. Taking Q0 over Qi is just the same as H over Qi. So in this case, what is the sum?
For the S, the variable.
You have to make this 1. Okay. Multiply all of the terms by R0. Any question? So let us see the effect block diagram of polar revolution. So HSP comes here, yeah. Plus output.
What is it? What is it? Is it QI? The HSP. Just going move.
QI is an input to the plant, not input to the whole system effect. HSP is the input to the effect.
So the QI is H time A.
QI?
QI is H time A.
No.
QI is HSP minus H time A.
Yeah. You have to subtract HSP and then multiply by K. QI is error times K. Error times K is the. So what is the input to the controller? This is the controller. What's the input to the controller?
Error.
Error, that's correct. What is the input coming to the plant?
UI.
UI, you know, right? What is the input to the whole feedback system? HSP. What is the output of the controller?
QI.
UI. The output of the controller is UI. What is the output of the plant?
HS.
But you have to know this the basic level. What's the from. Let us do PI controller here. Then we set the HSP to the step function at 0. Cannot be slow because we have to do quiz after this, yeah. But what we want to do in here, how do we get the feedback transfer function? Also transfer function. How to do it? Just do it. Yeah. What is the G? That case?
Controller at one.
This one controller by this one, that's the G. The 1 plus the G. That's manipulate.
Like H.
Let's see the next slide for the final value theorem. We'll use the final value theorem. Get the steady state value of I. Finally, get it start. The final time of the system is the same as the steady state error is 0. This one is 0. Second is this one. What is one? This one to the third. Okay. So that's correct. Multiply all of the S terms.
Anything that has with this. Actually getting now.
But you have to eliminate the S first. Don't put S here. So 0 and then anything that you can cross plus S. You cross it first, after that you replace. So it seems that the quiz, no, this is not the quiz. Not the quiz. One is coming for one input. I will keep the hangout for this. For yeah. All of the exam problems last year. The exam next year will be different. How to do this? Combination. You are given the transfer function, then you have to draw the block diagram. You add your brand. Yeah. There are two inputs. There are two. What about this one?
So that the may I say?
Yeah. Right. Only 1 minute. Yeah. 1 minute.
Oh. Okay.
Well, no, C1 is not there.
Oh,
You is the
C1
output.
Oh, yes.
Very pizza.
So, like this, acceptable or not, sir? Okay, okay. Open again, open again. Open.
The pizza.
You know what? The G3 may become block. Oh.
Can anyone do this one?
You do this.
Can anyone do this? Right.
Oh, because we have MATLAB. There's another problem here. Oh,
Yeah.
Yeah.
Right?
Yeah.
Really explain this. Really explain this one. This one.
Oh.
Very easy. This one.
G3.
And this one you make with this. This is the sensor. Oh, I think I get it.
Good.
Yeah, I mean that's.
The feedback is wrong. Yeah, tadi. The feedback line is wrong. The feedback line is wrong. Yeah, it's.
Oh, yeah. Kan
Yeah.
because you do that one first, baru times G3.
Yeah.
Plus.
G.
Plus.
And that's correct. Okay, that's good. Okay. And then Stephen also correct. Can anyone combine it?
Goodbye.
Bye. All participating students will get points.
So, cannot tadi satu blok. Too simple.
Yes. That's why I asked sir. Usually from complicated shape to years following can we use the same method to change the simplified shape into
How much we use the algebra?
Because when you are given just the transfer function like this, you are right now. There are multiple solutions, more than one solution.
Double disaster.
Double
disaster.
Yeah, this is okay, although this should be minus.
Oh yeah.
Can anyone think if we put the G3 only one block only?
Yeah, so this is eliminate the error, sir.
Yeah.
Errornya nggak di situ aja.
Errornya dari gitu. Jadi kan gitu naik ke atas.
Oh.
Ya, gitu.
Yeah.
Then move the G3 to here. If you move G3 to there, what happens? Are you thinking of removing G3 from there? Because that's correct. Yeah, that's how to do it. Yeah, you move G3 from there, and then you can beyond the.
So only
Habis there. Okay. This is correct. Okay. Okay, that's for the number one, yeah. And then number two. So number one is this one and this one. That's number one. And number B is this one. So 5 points, you get 2.5, 2.5, until get 10.
Yeah. Sir, I suck at sir. Yes, sir. People cannot do it without us.
Before the quiz, I want to show one more thing.
Because if the denominator is plus, that means the error is negative. If it's negative, that means the opposite. In the block diagram, I don't know.
I don't know.
Do you know what happened if we put this should be minus? If we put it minus,
Plus, a little bit.
yeah, the system over there become plus. If we put plus, over there become minus. The system become unstable. Sometimes the arrangement like this, that you know, yeah, this is also called as negative feedback system. The feedback is multiplied by negative sign. Don't be confused. If some references call it negative feedback, that's very unusual. The thing that I want to show you. I bet that you never see transfer function a lot in your mind. Only a few times, right? Because in this class we should see a lot of transfer function, and Nathan will see a lot more. Captain, will also do it. Transfer function we're doing control. Transfer function has numerator and denominator form of polynomial. And the transfer function is called strictly proper if the power in the denominator is greater than power in the numerator. So for example, this one, power 2, this is power 1, yeah? So this is proper. One has the same power, yeah? Power 3, power 3. So this is proper. You can still work on this, but let's say the power in the low, the denominator is smaller, you cannot work with that. against the physical law. MATLAB also cannot simulate that. That's the question. I will give you in paper. So we will continue the class on Wednesday with